We already saw the disadvantages of multicarrier modulation. One of them was it was spectrally inefficient, and this disadvantage we can overcome this by using overlapping subcarriers. The other disadvantage which we identified was the need for n number of modulators. If you want to generate a multicarrier signal, then even if you have overlapping subcarriers centered at different frequencies f0, f1, f2, etc., up to fn minus 1, still you need modulators, you need frequency generators that that will translate these subcarriers to these sender frequencies f0, f1, f2 up to fn minus 1. And the third requirement was the need for precision low pass filters. Okay, and we'll see how we will overcome the other disadvantages also, and we'll also see that this thought process, it leads to the idea of OFDM, orthogonal frequency division multiplexing. So let me start with orthogonal frequency division multiplexing. Or in short, we'll say OFDM. So the idea of OFDM begins with the theory that complex exponentials are eigenfunctions of any linear system. So let me write that: complex exponentials are eigenfunctions of any linear system. Complex exponentials are eigenfunctions of any linear system. From this idea, all the concept of Fourier series and Fourier transform, etc., originated from this idea that complex exponentials are eigenfunctions of any linear system. So we can replace the carrier cos 2 pi ft with the complex exponential e raised to j 2 pi ft. Okay. In the multicarrier transmitter diagram, we had various carriers cos 2 pi f0t, cos 2 pi f1t, etc., up to cos 2 pi fn minus 1t. We can replace that with the complex exponential e raised to j2 pi f0t, e raised to j2 pi f1t, etc., e raised to j2 pi fn minus 1t. Okay, when I do that, my composite signal at the transmitter output, the composite signal transmitter output, which I denote by S of t, it becomes summation I equal to 0 to n minus 1 si of let me just denote it by si, and e raised to j 2 pi fi t. What are these Fi's? Fi is equal to F naught plus I into Bn, or F naught plus I divided by Tn, or I can write F naught plus I into B divided by N, where B is the whole bandwidth. Okay, B is the whole bandwidth of the system. B is the whole bandwidth of the system. Okay. So again, how can you overcome this disadvantage? The use of N modulators. So two scientists in Bell Laboratories, they thought of an idea, and their idea, let me represent it in the graph. Their idea was, you need to generate a multi-carrier signal. You need to generate a signal that is having addition of many subcarriers. So in order to generate that, what they did is, let me draw the MCM signal first. Let me draw the MCM signal, multi-carrier modulated signal. It has one particular subcarrier, one subcarrier. And it has the other subcarrier. Remember, when you draw these subcarriers, there should be, yeah. So when you sample this subcarrier, all the other subcarriers should be 0. When you sample this subcarrier, all the other subcarriers must be 0. It's like this. And when you sample this subcarrier, the other subcarriers are 0, and it goes like that. So this is F0, F1, F2, etc. up to Fn minus 1. F0 is a very high frequency. Remember, F0 is a high frequency. Separation between F0 and F1 is just 1 by Tn. So F1 is F0 plus Bn. F2 is F0 plus 2 times Bn, etc. etc. Fn minus 1 is going to be F0 plus n minus 1 into Bn. And the total bandwidth of the system, let's say that is B. B is the total bandwidth of the OFDM signal, or simply the total bandwidth of the system is capital B. So they had the idea that bring this signal into baseband. Okay, first of all, they brought this signal to baseband. Bring this signal to baseband. How can you bring it? I told you F0 is a very high frequency. You subtract that from this system, so the whole subcarriers, they get shifted to baseband. So baseband is basically low frequency. and you have subcarriers. Okay, when I subtract this, um, when I subtract f0 from this system, actually this gets shifted here, but it doesn't look really good. So let me just draw it from here. Imagine that this is zero frequency. You have subcarriers like that, just like before. Well, only thing is now it is baseband OFDM. We have brought things to baseband, or I haven't reached OFDM yet. So let me just say baseband multicarrier modulation. Okay. So I have here zero frequency. I have here Bn. I have here 2 times Bn, etc. Goes up to n minus 1 into Bn, and you have n number of subcarriers, each of bandwidth Bn, and so the whole bandwidth of the system is B itself. That doesn't change. You have only done a frequency translation. You have brought things to baseband, but you have not changed the bandwidth of the signal. And now modulate each of these subcarriers with symbols. Multiply each of the subcarrier here with symbols. So this symbol, maybe it is S0, this is S1. Okay, I'm writing capital S0, S1. It's a convention to use capital letters in frequency domain and small letters in time domain. This is S2, etc. It goes up to Sn minus 1. So you have n number of modulated symbols. All these are modulated symbols. S0, S1 up to Sn minus 1. These are modulated symbols. The modulation can be any PSKs, or it can be any QAMs. So these are modulated symbols. And I have these modulated symbols modulated at these points. They are basically multiplied at these points on the subcarriers. They can be considered as data in frequency domain. Okay, that is another way to see it. Basically, this is frequency axis. So S0, S1, S2 up to Sn minus 1. They are of course they are frequency points. They are the values of this signal at f is equal to 0, f is equal to bn, f is equal to 2bn, f is equal to frequency equal to n minus 1 into bn. So S0, S1, S2, they are the values of this signal at these points, or you can see that as frequency domain data or data in frequency domain. Okay, S0, S1, S2 up to Sn minus 1 is basically data in frequency domain. And when you add all these subcarriers in frequency domain, how it would look like. So it would look like this. And here you see only this signal has this value S0. All the other signals are 0 at this point. They have their 0 crossings. And this would look like, it happens at every center frequency. Only that signal will have value at that point. All the other subcarriers will be 0. And the signal would look like this. Okay. So typically a OFDM signal will look like this. If you see the frequency spectrum of OFDM signal, it would look like this. Addition of subcarriers. Basically what happens is addition of subcarriers. Okay. And if you plot OFDM signal in MATLAB, you will see that the spectrum looks like this. Okay, some ups and downs, and that is a frequency domain. And it happens due to addition of subcarriers in frequency domain. And these points are very, very important. These points, they are the data points in frequency domain. They are simply the data points in frequency domain. And when you have subcarriers, the subcarriers cannot abruptly stop here. In practically when you see it, it will have a small tail like this, and but the 0 crossings definitely will be along this point. For example, this signal, it will have its 0 crossing point here. This signal will have its 0 crossing point here. So at the point of sampling, even if there are there is some tail which extends to both sides, at the 0 crossing point, all the subcarriers will have 0 crossing points at these sampling points, S0, S2 up to Sn-1. So S0, S1 up to S2 up to Sn-1, they are basically data in frequency domain, or they denote the data transmitted on the I can write SI. SI is the symbol transmitted on the ith subcarrier. SI is a symbol transmitted on the ith subcarrier. So, and I can vary from 0 to n-1. So you have n number of symbols transmitted along n different subcarriers. And how does it look in time domain? We'll see that also. How does it look in time domain? We cannot really have an obvious picture like this in time domain. However, let me just try to illustrate for completeness. So I'm drawing the time domain, and time domain is limited to Tn, some Tn. Tn is the time duration of OFDM signal. It is the time duration of OFDM signal, or it is the time duration of each of these subcarriers. So you can have the first subcarrier, okay, something like this. Could be of any shape, in time domain it can be of any shape. It's the first subcarrier. There could be another second subcarrier like this. There could be another subcarrier, right? Third subcarrier. And due to the addition of all these subcarriers, or one over the another, so you are adding all these subcarriers. So this is the signal in frequency domain. In time domain, you are actually adding all these subcarriers, and due to the addition of all these subcarriers, The resulting signal can have any shape. So there can be n number of subcarriers which are getting added on one over the other, and the resulting shape would be anything, could be any shape. Let's say this is the resulting shape, or I'll draw a little more beautiful shape. Yeah, this is the resulting shape. At some points, the signal may have constructive interference, where the subcarriers add with each other. Subcarriers, they have the same phase and they add with each other. At some points in time, the subcarriers may have destructive interference, where the subcarriers uh, subtract one over the other, and the resulting signal will have a lower value. And the resulting time domain signal, when you see in MATLAB, it looks very irregular. It might look something like this. Oh, it looks like a periodic one. No, it could look something. Okay, it's a very irregular signal in time domain. You cannot clearly see subcarriers in time domain because they have added one over the other. Okay. So now consider that this is your time domain signal. Now this time domain signal is your basically your multi-carrier modulated signal, but only thing is it is in time domain and you cannot clearly see the subcarriers because the subcarriers, they have added and subtracted one over the other when there is constructive and destructive interference. Different phases subtract with each other and same phases add with each other. And in time domain you have this OFDM signal which is very irregular in shape. Yep. But the thing is, it is time limited in the signal is time limited, right? It is limited in time. The signal extends from 0 to Tn. Okay, signal extends from 0 to Tn. So this is the time domain. This is the time domain OFDM signal, and this is the frequency domain OFDM signal. Yeah. Now, how can you get rid of n number of modulators? So you see, multi-carrier modulation showed that you can have n number of modulators, each having a center frequency, this, and you can add all this thing together. But scientists in Bell Laboratories, they came up with the idea that what you need to do is they observed a particular pattern here in the frequency domain, that this whole system is limited to bandwidth B, right? It is limited to a bandwidth B. When you have the system limited to bandwidth B, okay, the system is band limited. System is band limited to B. When you have the system band limited to B, according to Nyquist criteria, the sampling frequency must be equal to B. The sampling frequency must be equal to B, right? So when you have a system that is band limited to B, which means when the system is band limited to B, the sampling frequency should be equal to B. Or you might have learned in other way, when the system is limited to B, it is B by 2 and minus B by 2. In that case, 2 times the maximum frequency here, that is b by 2, and it is b. So according to Nyquist criteria, sampling frequency equal to b. For this signal, the sampling frequency equal to b. And you see, yeah. So if the sampling frequency equal to b, then what should be the sampling interval or the sampling time? Sampling interval Ts must be equal to 1 divided by b. Sampling interval or sampling time must be equal to 1 divided by b. Or I can write this as 1 divided by, what is b? B is equal to n times bn, because you know that the bandwidth of each of the subcarrier bn is equal to total bandwidth divided by n. So you have Ts is equal to 1 divided by b, or 1 divided by n into bn. This you can write 1 by bn is nothing but tn divided by n, which means this signal can be sampled according to Nyquist criteria. It can be sampled at a rate of at a sampling interval of Ts is equal to Tn divided by n. And what is Tn divided by n? Tn divided by n is, so this whole time period is Tn. This is Tn. You divide it into n different n equally spaced time points. You divide that into n equally spaced time points. That is Tn divided by n. So you have 0th sample here. You have first sample here, and this interval, that interval is Tn divided by n. And your sampling time, every Tn divided by n, you are going to sample this signal, and you are going to have n number of points, right? Because you have total time duration as Tn, and total time duration is Tn, and you are dividing that into you're dividing that into Tn divided by n time intervals. Tn divided by n time intervals. So you will have n number of points, sample points, n number of sample points. So when I have n number of sample points, Nyquist criterion says that I can I've taken the Nyquist frequency as b, and the speciality of Nyquist frequency is that if I sample at Nyquist frequency or even above the Nyquist frequency, I can uniquely recover the signal. Okay, so Nyquist says that if I sample at Nyquist frequency or greater than or equal to, if I sample at a frequency greater than or equal to Nyquist frequency, I can recover, I can completely recover the signal, right? I can completely recover the signal, which means that what I've done is I have taken the sampling period where the Nyquist frequency is satisfied, and if I have sampling points here, if I have sampling points in time, I have n number of sampling points in time equally spaced, I can completely recover this signal. The scientists in Bell Laboratories, what they thought was, why should I have n number of modulators in the transmitter side? What I need is, I need to generate these sample points in time. I need to generate these points, these equally spaced points, which are sampled in time, I need to have these values only, right? I need to have these values. So how will I generate equivalent time values from a frequency domain signal? And that is the process of IDFT. That is the process of IDFT, inverse discrete Fourier transform. Inverse discrete Fourier transform. From the frequency signal, I'm trying to generate the sampling points in the time. So I have n number of points here, which are sampled in frequency by a gap of Bn. Okay, my sampling gap here is Bn, and I can have an equivalent time domain signal. I can have this signal values in time domain by taking the IDFT of these values. In order to take the IDFT, I don't need this whole multicarrier signal. I just need these symbol values, right? I just need these symbol values only. I don't need the whole signal. So the idea of OFDM was to have modulated symbols in frequency domain, having these symbol values at these points. And by taking IDFT of that, I will have n number of points in time domain. Okay, I have n. We used to say if we have n number of points, if a signal is specified by n number of points in frequency domain, then we can specify the symbol with n number of points in the time domain also. So I can have same number of points here in the time domain by taking an IDFT of this inverse discrete Fourier transform. So from the frequency domain to a conversion from frequency to time domain, and consider that the points now I consider are discrete in nature. Earlier we were talking about the continuous signals, but here S0, S1, S2 up to Sn minus 1, these are the frequency domain data points, and they are actually, now I am considering them as discrete points in frequency domain, sampled by an interval of Bn. The time domain equivalent of this signal is we get it by taking the IDFT, and we have these sampling points, n number of sampling points in time domain, which I take using the Nyquist criteria, and I can completely recover this signal. I can directly make this signal by just having a conversion of frequency domain to time domain using IDFT. So I don't need n number of modulators. I just need these symbols. I take the modulated symbols directly. I do an IDFT, and I get this time domain sample values. And Nyquist says that these sample values, I can from the sample values I can completely recover the original signal like this. All right. So basically, what happens is that you know that if I take a signal in time domain and I do a Fourier transform, continuous time Fourier transform, I get the equivalent frequency domain signal. And if I want to sample the signal in frequency, what we used to do is a DFT. Okay, sample the signal in frequency, and I have some sample values. Let's say here in this case it is they are SIs, they are modulated symbols, and this I am taking a IDFT, and I get the time domain equivalent points, right? Small letter SI, and from here I can get back S of t. That's what Nyquist says. According to Nyquist criteria, I can completely recover these symbols. So in multicarrier modulation, we were dealing with this conversion, but in OFDM, we are now doing this. From the frequency domain, we are doing an IDFT to get the time domain samples, and from the samples, we are able to recover the original signal S of t by using a digital to analog converter. Okay, so this is the idea of OFDM, and we just saw that graphically. We can also prove this by using equations. That is, when you have the composite signal, S of t, which is equal to summation I equal to 0 to n minus 1 Si into e raised to j 2 pi Fit. What are these Fi's? Fi's are now this, if this is 0, this is Bn. So I can, in general, I can write Fi as I into Bn, where I goes 1, 2 up to n minus 1, right? So Fi is basically I into Bn, and if I am taking I am considering the nth sample in time domain, I will have S of n into Ts, where Ts is the sampling period, sigma I equal to 0 to n minus 1 Si e raised to j 2 pi. Fi is equal to I into Bn, and T is replaced by T into n into Ts, and this can be written as I equal to 0 to n minus 1 Si e raised to j 2 pi I into Bn. Ts can be written as 1 divided by B, or you can write it as 1 divided by n into Bn, and you see that this Bn and Bn, they get cancelled with one another, and now I can write as S of n, because now this expression on the right hand side, it is independent of Ts, so I can write this as I is equal to 0 to n minus 1 Si e raised to j 2 pi I n divided by capital N, and this signal is nothing but it is the expression for 2 pi I n by n. This signal is the expression for IDFT. Okay, which means that if you consider the nth point in this OFDM signal, you have this equation of IDFT, and that's very sensible. We used to take IDFT like this. You already know the equation for IDFT. The SI is the modulated symbols. So the idea of generating OFDM has become very simple. Idea of generating multicarrier has become very simple now. You just take the modulated symbols and perform an IDFT. So you have the time domain equivalent of that OFDM multicarrier signal. And when you're practically doing this, even in simulation or in hardware, IDFT is usually implemented using IFFT because it uses lesser number of computations. So in practical implementation, we use IDFT instead of IFFT instead of IDFT. Practical implementation, we use IFFT instead of IDFT, and you have this expression, nothing but the expression for OFDM signal. Okay, OFDM signal. And remember, this is the discrete OFDM signal. It is a discrete OFDM signal. If you want to transmit, you need to make it continuous in nature. And how will you do that? Let me take the block diagram of OFDM. This is the block diagram of OFDM transmitter. You have modulated symbols, serial data converted into parallel, x0, x1 up to xn minus 1. All these are your parallel data. All these are modulated symbols. These are all modulated symbols. And you do an IFFT in order to get the time domain equivalent samples, and add cyclic prefix. Okay, we'll talk about cyclic prefix later. And this time domain data that you get, it is converted into the discrete data. So what you get here is that these are all discrete values. These are all discrete values in time. And because I have sampled the data in such a way that it is equal to the Nyquist frequency, so I can recover the signals completely. And I do that using a discrete to analog converter here. I have a discrete to analog converter, it converts. And remember, we have baseband OFDM here. Okay, at this point you have x tilde of t, it is baseband OFDM. Baseband OFDM. You can see in the diagram, 0BN, it is baseband OFDM. You actually down converted this OFDM to baseband OFDM. So you want to convert it back to high frequency OFDM. So you want to do a frequency translation. Okay, you want to add F0 with every frequency. So basically you are trying to translate this frequency to the higher frequency. For that you have this multiplication, so cos 2 pi F0 t, which translates this baseband OFDM to our bandpass OFDM, or high frequency or bandpass OFDM. And we have covered the concept of OFDM. We have looked at that in time domain and in frequency domain. We saw graphically that we are able to do IDFT, and the sampling period must be equal to Tn divided by n, which is basically the total time divided into n number of points. And we saw that we have n number of points in frequency domain, and we can do IDFT, and we can easily convert this to time domain signal, time domain sample values. And these sample values, we have converted it according to Nyquist criteria, so we can totally recover the signal completely. And this recovered signal is finally made it into bandpass signal S of t, and it is transmitted. So this is the discrete implementation of OFDM. And in the next class we'll see what is the significance of this block, which is addition of cyclic prefix.